Swayam Prabha. Digital India. Educated India.
Good morning, gentlemen. Yesterday we were talking about the various formulations of engineering problems, and today let's talk about the solution methods. And then let us say these solution methods, as we keep telling, so these are all approximate solutions in the sense that the solutions which we get are approximate to the exact solution, and always there is an error, and this error can be reduced to as low value as possible, and depending upon the method. And in fact, that's what is going to lead to finite elements, where we say that as the number of terms, as the number of elements increase, as the number of degrees of freedom increase, then the solution will become better and better to any accuracy that's required. And here the approximate solutions. So let's look into some of the classical approximate solutions. So we have talked about T methods. One is the variation formulation, and the other one is direct differential equation approach. The governing equations are directly given in terms of differential equations, which need to be valid each and every point together with boundary conditions. And then the third one, I also mentioned that we have another method of formulation, that is the virtual work principle. Particularly, it is suitable for solid mechanics. So the classical approximation methods have been there for many years, and particularly let's start with some of the very popular approximate solution method for the variational formulation. Yesterday we talked about the variational formulation for the taut string problem. It's a one-dimensional problem where the string is under tension, and then there's a load, lateral load, vertical load, which is applied, and then we wanted to find the solution, that is the deflection. So let's take that, and then we will proceed to taking the equation, governing equation in the form of differential equation. So that is the second method, second approach for approximations. And then third one, we will take it up virtual work sometime later when we talk about solid mechanics application. So for example, here, what we were talking about is that as an example, so we are talking about the variation form, and in particular, as an example, we will take 1D taut string. So the formulation for this one is with regard to a string like this under tension, and to be in tune with the positive sign convention. So we take the string to be in the x direction, and then in the y direction, the deflection is positive, as well as the loads which are acting in the y direction is taken to be positive. So the variation form of this problem is, yesterday we said that it consists of the formulation in terms of potential energy, and the potential energy we have written phi as yeah. So this is the potential energy, and so W is the solution. And by any chance, if W is not the exact solution, say if W is approximated by some W hat here, and so then phi will be computed, and according to this theory, out of all the admissible set of functions for W hat, admissible in the sense that which satisfies the boundary conditions here, W hat has to be 0, and at x is equal to 0 as well as at x is equal to L, and out of all that, the one which minimizes this phi is going to be the solution. In the solution, in the sense that it also will satisfy the problem posed in terms of differential equation. So if you recall, so we have it as t into d square w by dx square plus q is equal to 0. That's the differential equation formulation, right? So that means that this solution will be the same as the solution that is obtained as a solution of that differential equation. So let's try to get the solution from this formulation. So to do this one, so what we require is that we need an approximate solution for W. So W is approximated as W hat, which is a function of x. So since we do not know the solution of W hat, in fact, we would like to take one term. Let's take one term, and then also we'll indicate how we can generalize it for more number of terms, in the sense that here we will take it in terms of polynomial terms. So let us say that it is x into x minus L, and say some constant here C1, and you can say here that x into x minus L is satisfying, that W hat is 0 at x is equal to 0, and satisfies this one. Satisfies W hat is equal to 0 at x is equal to 0, as well as it is 0 at x is equal to L. Okay. So what we are saying is that this the solution which we have assumed, and then there's a coefficient here C1, which is a coefficient which is undetermined, in the sense that if we go through the procedure here, so we will get a method to determine what is the value of C1. So that will give the solution. Okay. So this is one method. I'll tell you exactly what is this method. So this is known as Rayleigh's method, and so where the approximation is assumed like this together with the coefficient C1, and then this C1, if we find out, then that is the Rayleigh method. So then we can also approximate this one. We can have better approximation by choosing more number of terms. For example, we can choose, say, a two-term solution is assuming like this one, C1x, x minus L, as well as one more term minus x square into x minus L. So if this is Rayleigh and this is one term approximation is the original classical one, and then which is modified by Ritz to include more number of terms and making it more general. So what is the improvement in this one? So this is two terms which has another one more term here, C2 multiplied by x square into x minus L. Of course, you can see that overall at x is equal to 0. So this is 0 whatever by the values of C1, and it's also equal to 0 at x is equal to L, because this drops and this drops to 0. So this is still an admissible function. Okay, so if you just have this function, then it's called Rayleigh, and to be more general, if you can add more number of terms, it will give you more degrees of freedom, and you expect that you get a better solution. So, all right. So this is if this is so, then this approximation we will substitute into this one, like this one. So what we need in this to evaluate, so we also need dw by dx, and which is nothing but x square, so 2x minus L, and C2 x cube, so that is 3x square and 2L x. So this is the first derivative of w hat, and of course q is the load. Okay, so q can be any function of x, or for that matter you can also take q to be constant if there is a continuously distributed, uniformly distributed load. Okay, so now what we are going to do here is that we are going to substitute this into this potential energy. So this is the potential energy we can calculate here, and just for the sake of simplicity, let's take L is equal to 1. Let L is equal to 1, and then what we have here is a simple solution here. So let us substitute it here, 0 to 1 t by 2 times C1 2x minus 1 plus C2 3x square minus 2x square, right, and minus q times C1 x into x minus 1, and so the whole thing has to be integrated between 0 to 1. We assume x is equal to 1, and this is what we need to simplify. Okay, so you can expand this, quadratic it, and then the C1 and C2 are constant, so the integration has to be performed for 2x minus 1 square and 3x square minus 2x square and across terms. So let me just give you, so we have, I'll just I'll leave that as a part of an exercise. So it is c by 2 c1 square times 1 by 3, and twice c1 c2 1 by 6, and c2 square 2 by 15, and minus q 1 by 6 c1. So this is what pi is. Of course, here what we have assumed is we assume that q to be constant, So interestingly, what you can see here is that this potential energy pi, which is a function of W hat, so finally turned out to be simplified as consisting of the constants C1, C2. So that means that this is essentially this pi at this stage is a function of C1, C2. So what we need is that we have to minimize this pi by with respect to C1 and C2. So we can do this one. So this is 2 pi by so C2 is equal to 0 for minimizing pi, right? Pi hat this stage. Okay. So what essentially we have here, so if you do that, essentially you do the differentiation with respect to C1 first. So that means that this is C1 squared, so that's 2 by 3 here. And with C1, if you do that, it's 2C2 times 1 by 6. And this is minus 1 by 6 C1. So what we have here is that the first equation is E multiplied by 1 by 3 C1 1 by 6 C2 plus Q into 1 by 6 is 0. This is the first equation. And the second equation is E times 1 by 6 C1 2 by 15 C2 plus Q multiplied by 1 by. Okay, so these are the two equations which we get by minimizing pi. So we have these two equations. So if you want, we can even put it in the form of the matrix 1 by 3, 1 by 6, 1 by 6, 2 by 15, minus Q all right. So that's two equations which we get, and then we put it in the form of a matrix. So you can solve for C1 and C2, and what we get here is that C1 turns out to be for C1 and C2 we get C1 is equal to minus Q to T, and C2 happens to be 0. So these are the two coefficients which we get here. And so finally we have W hat is equal to minus Q by 2 T okay. So this is the solution. So that means that out of all the possibilities of C1 and C2, the C1 taking minus Q by 2T and C2 taking 0, so this will minimize the potential energy, and this is the solution. Well, I will say that this is the solution, I don't call it. This is the best possible solution under the assumption of two terms. So you can very easily extend this argument. So you can add one more term, a third term, C3. For example, you can also add one more term here, okay, a third term, by taking the term, what is that? The possibility is that C3 into x cube into x minus L like this. So you can go on increasing the accuracy of W hat. You can see immediately that as I keep on increasing more and more number of terms here for W hat, the potential energy calculation here of pi so keeps on decreasing. So as you increase the number of terms to infinity, so the pi hat will reach minimum most value, and that is the, then we call it as the solution. So in fact we can also see here that if these terms, so it's also important that these terms which we are adding more and more are going to be systematically better and better. You can, very interestingly, you can see that these terms here, x into x minus L is there everywhere, whereas the one term which is multiplying is 1 here, x here, and x square here, and x cube, x to the power of n. So they are systematically, we are building up higher and higher polynomial degree terms. So in fact this immediately will tell you that these are nothing but a Taylor series kind of approximation terms, right? So you can see very easily that since Taylor series themselves are complete set, they are going to give you a convergent solution with error becoming smaller and smaller and becoming 0 for any approximation function. So that is the beauty of these things. So in fact that also will suggest to us that the approximation which we do here has to be systematically better and better. So we are taking the polynomial terms as if we are choosing it out of Taylor series. We cannot choose it anything and everything. We have to see a complete set here, maybe a Taylor series. But on the other hand, if you take other kinds of terms like sin x is equally possible, right? So the other approximation here, other possibility, I will write here. For W hat is what? It is C1 sin pi x by L if you want, and C2 sin 2 pi x by L, and C3 sin 3 pi x by L, and so on. So here again, the interesting aspect which you have to appreciate is that we are choosing the term sin pi x by L. Obviously, it is going to be 0 at x is equal to 0 and L. Then we have chosen the next term sin 2 pi x by L. Exactly again, it is 0 and at both ends, and higher and higher order terms here. So you can immediately see that. So whatever be the values of C1 and C2 and C3, so this satisfies the boundary conditions. In fact, that is the precondition that it has to be an admissible function. So again here, you should appreciate that the terms which we are choosing here are trigonometric terms, and these trigonometric terms comes under the class of your Fourier terms. Again, the Fourier series are a complete set. As you keep on increasing the number of terms, so the approximation here which we are using is going to be getting better and better, because we know that Fourier series are a complete set and the error can be reduced to any small value as you desire, as you take more number of terms. So this is the, in fact, this is the thing which we are going to follow all the time. So we should make sure that as the number of terms which use increase, so we should make sure that the approximation gets better and better. So this is another set which is equally possible. So then you might ask me that is this a better set or is this a better set? In the limit as n goes to infinity, both of them are equally good. But as the number of terms are limited, if you are taking only one or two, so then it depends upon how close it is to the approximation is the one which is going to govern the accuracy. For example, here these sign terms are closer to the exact solution. So that is why if you use these terms, so you are going to get a better solution for n is a smaller number of terms. Okay, so this is the how we can do a Rayleigh-Ritz kind of approximation. So this is also important. In fact, we are going to use all these methods wherever they are suitable. So you should be conversant, you should have a command on these things very well. Okay, so now this is from the variational point of view. Now let's look at the another method where we are given the problem in terms of differential equations straight away. So let us see that. So the second method is called method of weighted residuals. So this is called a method of weighted residuals. So let us see what it all means. So in the differential equation type of formulation, what we have is a governing differential equation which need to be satisfied at each and every point together with the boundary condition. In fact, more generally, so we'll write it in this fashion. So I'll just explain it to you. So this is L phi. L is an operator, differential operator, and phi is a variable, primary variable, which we are interested in finding out. And then f is some function is equal to 0. So I'll just explain you with an example just now. And this is valid, should be valid at every point in the domain. So this is valid at each and every point. And then this is the boundary condition m phi plus g is equal to 0. So m can again be a differential operator. If you want to take the example of your heat conduction or even the torsion or even membrane, so let's try to identify what these terms are. So if you apply to say a heat conduction problem or maybe a membrane, I'll write both. So as an example, so we have seen yesterday that if you have a membrane here, just like a taut string, what we said was it is T times dou square W by dou X square plus Q is equal to 0. So this is what we said, right, where W was a deflection. Let's write it in terms of phi instead of W. Let's rewrite it. W as phi. This is more convenient for us. Okay, so we can write it as T times del square phi plus Q is equal to 0. Okay. And if you want, we can even rewrite it as del square phi plus Q by T is equal to 0 anywhere in the domain omega. Okay. So you can see here that this is the governing equation, right? And so if you can identify it with posing the problem in this manner, so we know that means that L is equal to del square operator and F is Q by T. And what is the boundary condition here? The boundary condition here is what? Phi is equal to 0 on gamma. So can you identify what M is? So M operating on phi and plus G is equal to 0. So here if you do this, so that means that M is equal to just 1 and the function Z here as written here, it is simply 0. So this is governing equation as we can governing differential equation, and this is the boundary condition which we can identify. So I think I'll stop at this moment and then we'll continue this one with one other application, the heat conduction problem, and then we'll proceed what is the things that are hidden in this one, the important facts of this method of weighted residuals. Okay, so bye for present.